All right, Math 189, first video. Welcome to my garage, somewhere in Boise. All right, so I'm just gonna introduce logic one, a major concept that we'll deal with a lot in logic is logical equivalence. That's what this video is about. This video is about this super important concept, logical equivalence. Okay, to introduce the idea of logical equivalence, I'm going to use one of De Morgan's laws. De Morgan's laws you'll use a lot in computer science, so might as well use that here. If you haven't used De Morgan's laws yet, you will, so don't worry. Okay, so two logical expressions are said to be logically equivalent, or in other words, two propositions, P and Q, or something you might call statements. A proposition, otherwise known as a statement, is a sentence that can be evaluated as true or false. It doesn't have, there's no gray area. It's either it's true or it's false. So two logical expressions are said to be logically equivalent if the final columns of their truth tables are exactly the same. Okay, so what I'm going to do here is I'm going to prove that this first De Morgan's law, that the negation of P and Q is the same as, now you would like to write equals, right? You would like to write equals. But equals doesn't really make sense for logic. So we have a special symbol that is a lot like equals. It's that, okay? This is, basically it's equals for logic. All right, notice that when you distribute the negation through, it changes the and to an or. Okay, I'm going to prove this with the truth table right now. All right. Okay, so what I'm going to do is I'm going to make a truth table for this and a truth table for this. I'm going to make it, I'm going to use the same truth table, and you'll see that the final columns, that the column for the truth of this and the column for the truth of this, the truth or falsity of this, the truth or falsity of this are the same. Okay, and that's logical equivalence. All right, so let me make that truth table now. All right, so we've got P, Q. So I'm going to make a column for P, a column for Q. All right, so look, we have a not P and a not Q. I'll make a not P, a not Q column, a P and Q column, a not P and Q column, and a final and another column, my last column, the not P or not Q column. All right, so let me go like this. So I'll go like this. Okay. Now think about it, right? We got P is a sentence that can be evaluated as true or false. Q is a sentence that can be evaluated as true or false. So we're going to exhaust all possibilities. We have, and easy way to do that is to do true, true, false, false, true, false, true, false. And notice that all possibilities have been exhausted here, right? We got true, 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 false, false, true, false, false. So that's all the different possibilities we could have. All right, so the negation of P, if it's true, then it's false. So we got false, false, true, true. Let's see, Q, we have false, true. Let's see, if it was true there, then it's false there, then it's true there. All right, P and Q. Remember, an and is true only when both statements that are put together or propositions that are put together are true. So true and true is true, true and false, false, false and true, false, false and false, false. Okay, now we'll negate this column, the negation of that. So we have false, true, true, true. And lastly, not P or not Q. So we're going to look at the or of these two columns. False or false is false. False or true is true. True or false is true. True or true is true. Now look, these final two columns are exactly the same, right? No matter what our choice of possible variations that there could be, whether it be true, true, if we have true, true, then they're both false. If we have true, false, then they're both true. We have false, true, and they're both true. False, false, they're both true. They're the same. Okay, so same. Means logically equivalent. This is logically equivalent.